This demo focuses on managing variability with model-based design and variant manager. I am covering three important topics in this demo: variation complexity, impact of variability on software development process, handling variability using model-based design and variant manager. This demo is on an automotive application, which includes handling variability in sensor modeling, control algorithm, and in actuator modeling. Products are categorized by a multitude of functional variants. So there are numerous sources of variability. For example, if we consider an automotive application, there is variability due to market and localization related topics. There is variability due to segment and vehicle type topics. And there is variability due to cost and buyer personas and versions. And also, the technical features drives numerous variable points or variabilities. The functions and the features drives the variable conditions, different kind of variabilities in the application. Other than this, we have many more other factors which create variability or variance in any of the application. If we consider a use case where we have 4 segments, 5 systems, 15 components, and 4 options, then so we'll have hundreds of combinations. An exponential combination growth with more variations. So this will lead to a very complex system. Variability is applied to different areas. It can be mechanical component, electronics component, software components. Offering of different technical features results in different ECUs. Functional variability in vehicle results in variability in software. Economic influences on variability motivates systematic reuse of software assets like architecture, specification, components, documentation, tests, and many more. So variabilities in software can be due to functional and feature availability. So where we enable certain features or disable certain feature or functionality. Configuration parameters, calibration parameters also add to the variability. And then the structural variabilities, which includes like conditionally executed blocks, enabled blocks, or signal routing blocks, or logical blocks, or configurable blocks. So we have functional and feature variability, that's the variation point. Configuration parameter or calibration variability, that's the variable parameter. Structural variability, that's the variable mechanism. So functional or feature variability management can be done using permanently coded or hard-coded parameters. In this case, we need to reflash the software parameter set every time when we want to change. And for example, the curtain and knee airbag systems features availability in a vehicle. For variant A, it's not enabled, but for variant B, it's enabled, but with the same ECU. And same case with vehicle limp home mode support. So this feature is supported for variant A, but not supported for variant B with the same ECU. In such a way, the feature and functional variabilities are becoming complex as the complexity of the vehicle is increasing. The same parameter can take different values set for different vehicle or different component or different ECU. And same way, so we can have like multiple structural variability inside a software or control algorithm, where so we use different parameters, so we use different signal values, so we may have prediction logics, and this can be applicable to functionality or parameters. So variability in the product requirement, like market needs, segment requirement, cost requirement, technical feature, influences the development process. That's a requirement which can be functional or system, design, high-level design or low-level design or mechanical design, system, software, and hardware architectures, unit component or system implementation, tests, and deployment. Now we can look into how variants can be handled using MATLAB and Simulink. So variations in requirements can be handled using requirement toolbox. Variants in architecture can be handled using System Composer. Variations in data, parameters, and variables can be handled using Data Dictionary. Implementation variations can be handled using MATLAB and Simulink and code generation aspects. And the test variations can be handled using Simulink Test and Simulink VNV. When we consider a large-scale system, variant management can be handled using Variant Manager. where we can create, manage, and activate different variant configurations, variant constraints, and we also create variant configuration automatically. We can reduce the model for a specific variant configuration. We can visualize variant implementation hierarchy. We can visualize variant parameters, configurations, and then compare different variant configurations. We can also simulate models with different variant configurations, and also we can run tests as well as generate code for specific variants. Let's look into this demo. In this demo, I'm covering topics with respect to managing variability in requirements, architecture, implementation, and verification and validation. Let us consider different requirements on the different configurations for a Viper system. So we can have front and rear Viper, manual or manual with sensor, automatic sensors, and we can have rain sensor, fog sensor, dust in both cases. And the same system can be applicable for North America, Europe, India, rest of the world, and many other configurations like sedan, cowper, SUV, pickup trucks, and automatic transmission, manual transmission. There are multiple configurations and variations for the system. This demo covers how these different requirements or variations can be handled using Requirement Toolbox, Simulink Data Dictionary, System Composer for architecture, Simulink and Stateflow for implementation, verification and validation toolboxes. To manage variability in requirements, Requirement Toolbox is used. So variant attributes are coded in custom attribute section or imported via Reki files or from any other requirement tools. Variant code is applied to the respective requirement. Variant code defined in the data dictionary is mapped to the requirement. Implementation and test cases are linked for the traceability in the requirement toolbox. In the requirement toolbox, requirement editor, we have elicited all the requirements and the variations in the drive mode, region, and vehicle type are coded as custom attributes. And also the variant parameters for each variations is coded here as a value. All the requirements in requirement toolbox are mapped to respective variation code or variant code in the data dictionary, and also to the architecture and also to the implementation. So in data dictionary, which manages all the parameter variations and configurations, all the requirements for the variants are defined. The data dictionary gives an overview of all the variants and variant parts. So we'll be able to perform a variant dependency analysis and hierarchy using this. Variant maps, where we handle map variations, and the handling calibration parameters also done via data dictionary. In data dictionary, we have defined all the variant variables, variant parameters, variant controls, and also variations which is applicable to architecture, and everything is coded and everything is defined in the data dictionary, and also it's mapped to respective requirements and to the implementation. So variants with respect to architecture, so we have defined variants in architecture using System Composer. So we can use variant manager to view and create different configuration for the architecture. So it is applicable for both system and software architectures. And also we can map requirements and we can have the traceability overview. This is the architecture model. So we can see the requirement which is mapped to this particular architecture. And we have sensors, driver commands, control algorithms, motors for rear, front, and splash systems, and also the control algorithms here. So in case of sensor, we have multiple sensor defined here as a variants and as a variant blocks. Let's look into the sensor models. So we have rain sensors, fog sensors, snow sensors. In case of rain sensors, we have 4 variations. So rain sensor has got 4 variations like sensor model 1, 2, 3, 4. Similarly, we have variations for other sensors model also. And also for the front and rear motors, we have variations. And if you look into this one, all the configurations using Variant Manager. So this is how it looks. So all the possible combinations are reflected here. And also we have control expressions associated with each variant. And so we can also generate configuration based on the values which is available here. So I'm generating the configurations now. Okay, it's generating configurations. So it already generated configurations with possible values for all the variance controls. So I will close the configuration now. So this is the implementation model. So in this model, the control algorithm, sensor processing algorithms, the commands, and the motor and the plant models for both front and rear motors, rear wiper system is implemented. The control application is here for front, rear, and splash system. And we have multiple testing points where we can test these algorithms based on like different kind of inputs. Let's look into the implementation model. So front wiper has got the driver input processing logic and also control logic for wiper motor control. And it has got different kind of variations or variant management techniques like variant source, variant sync, and other variant blocks. And similarly, the different sensors like rain, fog, and snow sensor has got multiple options. So every sensor is modeled here. And we have two different plant model for front and rear wiper systems. And there is a simulation of environment where we simulate snow, fog, and rain using our 3D animation capabilities. So in this model, implementation model, we can view all possible variant combinations and variant or controls using Variant Manager. And also, we can generate the variant configurations based on different values. So I'm generating unique and valid variant configurations. Now, the Variant Manager has created 36 configurations with different possible valid and unique variations. So we can use this one for testing, generating code with respect to different kind of variant requirements. And the variant parameters helps in defining different parameter values based on variant conditions. These variant parameters for the implementation models are defined in data dictionary. Overall, to address different variations and to model variant in Simulink, so we have multiple options and different kind of techniques. The requirement variants are modeled using custom attributes. Implementation variants are modeled using Simulink. Architecture variants are modeled using System Composer. And Variant Manager is used for monitoring, managing all the possible variant aspects with respect to an implementation or architecture. And let us run this model now. In this simulation, we have environment plus the system. With the implementation, the models like system architecture and the implementation models using Simulink. So we can monitor only the rear wiper, or we can look into only front wiper. And different environmental simulation can be visualized using Simulink 3D viewer. And the parameter for intensity of weather is stored in data dictionary. Thank you.